Well, good afternoon, everybody. Welcome back to the Red Cedar Conference. We hope you have enjoyed what you've seen and heard so far. We know people are hopping back and forth between the Red Cedar and some of the other events that are happening in connection with Water Week. But we here in the Chippewa Valley and Red Cedar area are glad that you're around to share the information and the experience that we have to share with you. And speaking of that, our next presentation is about the natural history of the Red Cedar River. And our presenter today is Dr. Doug Faulkner. Doug is a professor in the Department of Geography and Anthropology at UW-Eau Claire. He's been here since the fall of 2000. Before that was an assistant professor in the Department of Geosciences at the University of Missouri, Kansas City. And before that, a grad student in the Department of Geography at UW-Madison, where he earned a PhD in 1994. His area of specialization is fluvial geomorphology, which simply means he studies flowing water, especially rivers, and its land-forming effects. He's interested in how rivers change through time, particularly in response to environmental change, both natural and anthropogenic. So take it away, Doug.
All right, thank you, Dan, and thank you all for coming, whoever is out there in Zoom land. So this talk is on, as it says, the natural history of the Red Cedar River, but I have a few admissions to make at the outset. As Dan said, I am a geomorphologist. So what is a geomorphologist? So here I am, and I was a lot younger then. I study landforms. Geomorphology is literally the study of land or earth forms. And of the processes that create them and modify them over time. And again, as Dan said, I am in particular a fluvial geomorphologist, a big word, as a friend of mine said in grad school, a big word's little concept. Fluvial just means river or flowing water. And so I study rivers, or more broadly flowing water, and the effects on the physical landscape. So this natural history I'm going to talk about is a natural history of the physical landscape. Often the term natural history, think of maybe the history of vegetation or animals, how they change through time, maybe migrate, adapt to climate change and the like. But no, I'm interested in rocks and dirt and stuff, and especially that which is affected by flowing water. So maybe a more honest title to my talk would be Geomorphic History of the Red Cedar River. As what I do is I take and study the landscape, looking for evidence, hints of what it used to be, and attempt to reconstruct, based upon physical evidence in the landscape, what was here in the past, what we see today, how it came to be. So I'm sort of an earth historian of a sort. Now, earth scientists, which I am a part, many of them study earth science going back hundreds of thousands, millions, even billions of years. I don't go that far back. I only go back, say, I don't know, 20, 30,000 or so years. So that's what we're going to be considering here today, is the history of the Red Cedar and of the landscape it has helped create over the last, say, 30,000 years. Now, I have one other admission to make, and that is my research, the research I've done since I've been here at UW-Eau Claire since 2000, has focused not on the Red Cedar, but rather on this river, or looking downstream at the Chippewa River. And so much of what I am going to talk about today is going to really focus on or be derived from what I have done on the Chippewa. But that said, just want you to keep in mind, and I'll stress this throughout, that the Red Cedar and the Chippewa together, they are part of a system. One affects and influences the other. The history of one is the history of the other. And I'll explain that as I go along. One other thing I want to say before I get into the meat of the talk is that the research that I'm going to present here in a hopefully accessible way is, or was, or it has been made possible by collaborations with a lot of people. In particular, these two colleagues of mine in the Department of Geography and Anthropology here at UW-Eau Claire, Gary Running and Harry Joel. They're also geomorphologists, but of different stripes. Gary is a soils geomorphologist and geoarchaeologist. Harry is a geomorphologist who works with a lot of other geomorphologists employing a certain technique, something he has on his chest. This is right here. It's part of a system called ground penetrating radar. It's a way of looking passively or non-invasively at the subsurface, because the subsurface often contains hints about how landforms came to be. So they participated with me and have contributed a lot to this work. I would be remiss if I didn't give some props to a whole host of students, undergraduates at UW-Eau Claire, who participated in our undergraduate research program. Many of whom, there have been many of whom who have collaborated with me and Harry and Gary on our research in the Chippewa Valley and in the region. The photos here, this is actually not complete. There are a lot more students than I could fit on this slide, but a lot of them have been involved, made very significant contributions. And some of them actually gone on to become geomorphologists, well-known geomorphologists in their own right. Just want to highlight one, Phil Larson here. He's now a professor at Minnesota State in Mankato, a fluvial geomorphologist who is doing great work and is still collaborating with me. All right, so let's set the stage. So here's a map, obviously, of the upper Midwest, showing our water-rich region, especially the water-rich state of Wisconsin. And we see on this map the river which this talk is focused, the Red Cedar River, right there. Now, the Red Cedar is a tributary to a larger river, a larger stream, of course, the Chippewa River. The Chippewa River would be called the main stem of this stream system or stream network. And the Red Cedar is a tributary to the Chippewa, its largest tributary. Now, the Chippewa is in turn a tributary, obviously, to the Mississippi River. So the Red Cedar and the Chippewa's other tributaries all drain water from the landscape to the Mississippi River. They don't just drain it from any landscape, they drain it from this area right here. This red outline outlines the watershed of the Chippewa River, an area of land about 25,000 square kilometers, or about 9,500 square miles. So precipitation falling on this area, that which doesn't evaporate and transpire back to the atmosphere, eventually becomes water flowing in the streams. And those streams all join the Chippewa and flow into the Mississippi. Now, the Red Cedar, of course, has its own watershed. It's just a subset of the larger Chippewa watershed. It's about a fifth of the Chippewa River watershed. And it joins, as we can see here, the Chippewa fairly close to where the Chippewa flows into the Mississippi. Now, where this watershed or these watersheds are located is of great importance to their history. I'm going to put on here, I'm going to get rid of the words just to take some clutter off the map, a little dashed line, well, fairly long dashed line, a dividing line, if you will. Dividing line, dividing land to the north, the northern part of the Chippewa and Red Cedar watersheds, and to the south. And of course, we see this dash line sort of winding around here and doing all sorts of interesting things. But we're going to focus on this right here. So zoom in, and there are the watersheds, the Chippewa and the Red Cedar watersheds. And there is that very important dividing line. Now, what is that dividing line? I'm guessing many of you realize just exactly what it is. If you look to the north of it, you see, well, there's a lot of water up there, a lot of lakes up here, 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 and the like. Now, to the south of it, well, there are some lakes, such as that's Lake Wissota. Over here is Mahnamen and Tainter, some various ones on the Wisconsin River over here, but those are all lakes that are there because of human-made plugs in the river, dams. To the north of that, all those lakes, not all of them, but most of them are natural, maybe enhanced by dams, but they're part of the landscape. So what is this dividing line? Well, this dividing line marks the edge of a very large ice sheet that once existed in this part of the world. A large ice sheet called the Laurentide Ice Sheet. Now, the Laurentide Ice Sheet, part of the last ice age, is an ice sheet much like what the ice sheet of Antarctica is today. It started to form around 100,000 years ago as global climate cooled, with snow, annual snowfall not melting completely during the summer, especially in the area around Hudson Bay in eastern Canada. And over time, snow didn't melt, it piled up thicker and thicker, and it started to compress the deeper layers, compressed it into ice. As the snow continued to accumulate, got more and more ice, the ice started to flow under the weight of the overlying ice and snow. It was a glacier then that flowed out of this region right here, the Hudson Bay region, in all directions, including flowing to the south into what is now the north central and northeastern United States. Now, when the Laurentide ice sheet flowed into the United States first, we don't really know. This may have happened. There may have been some warming that it retreated, but we do know the last major advance happened around 30 or so thousand years ago. And at that time, around 30,000 years ago, Laurentide ice advanced into the Chippewa River watershed. Now, what's shown here then is when the Laurentide ice sheet was at its maximum extent. It's called the last glacial maximum, or for those in the know, just the LGM. The LGM has been well dated by a variety of techniques around the world. It happened at around 21,000 years ago. So this shows the extent of Laurentide ice at 21,000 years ago. And at that time, we have the Chippewa River, and we have the river it flows into, the Mississippi River. Though much of what is the Chippewa and the upper Mississippi today was under ice. Now, these two rivers, back at this time, and before this, when Laurentide ice flowed into their watersheds, these rivers were dramatically different. The landscape was dramatically different. So here is a view of what it may have looked like back then at the edge of the Laurentide ice sheet. This is a photo of the Greenland ice sheet, but it was probably very similar. Looking up to the north, rather thin ice at the edge, thickening to the north. In fact, getting so thick that by the time it got to around Hudson Bay, or even before then, the ice was over 2 miles thick, much as it is in Antarctica today. This ice just didn't stay there year-round in a frozen state. Summer still occurred. And during summertime, melting happened. And when melting happened, started to get very dirty ice along the edge and water flowing out from the glaciers, often flowing out through tunnels in the glacier. Now, this water that's flowing out wasn't clean water, but it was chock full of sediment, gravel, sand, and finer grained material coming out in this glacial meltwater. And away from the glacier's edge would have been streams of water flowing away that were flowing in a variety of channels that shifted all over the place, a kind of streams called braided streams. So this is what the Chippewa River and the Red Cedar River, which also was a glacial meltwater stream, and the Mississippi River, this is what they would have looked like back at the time of the LGM. Now, further down valley, these braided streams would have persisted, flowing through a landscape of tundra and permafrost. So this is what it would have looked like, say around 20, 25, 30,000 years ago. That is, if you take away the mountains. This is the Chippewa River. This is the Red Cedar River. This is the Mississippi River. rivers that were glacial meltwater streams. Now, as I said, these streams carried an abundance of sediment that was coming out of the melting glaciers. In fact, so much sediment that they were what is called overloaded with sediment. What that means is they had more sediment in them than they were able to transport downstream. And so what happened, the result of this is that the streams aggraded. What this means is that they slowly but surely filled their valleys, mostly with sand and gravel. During times, a channel would fill up with sediment, causing the stream to spill out of its channel and carve a new one. And that one would fill up with sediment. And this went on for decades, centuries, maybe even several thousands of years, filling the valleys of the Red Cedar River, the lower Chippewa River, the Mississippi River with glacial sediment called glacial outwash. So that was about at the time of the LGM. Now, after the LGM, global climate started to warm, somewhat in fits and starts, but it warmed, and as it warmed, the glacier started to retreat, started to melt away. As more ice in a given year would melt, then new ice would form. And so by around 14 or 13,800 years ago, the Laurentide ice sheet had shrunk back to about this size. Still have the Mississippi River there, the Chippewa, but now, by this time, the Chippewa may have not been getting any glacial meltwater. Around 13 or so thousand, 8,000 years ago, the glacial ice had retreated out of its watershed. And largely, that's true for the Mississippi too. Maybe there was some in a few places, but not much, not directly. However, there's one other feature on here that I want to point out, is that a number of lakes that started to form along the margin of the retreating ice. Lakes where the slope of the land was down towards the ice so that meltwater from the ice could accumulate. One of these lakes was, as you can see, between what's now Wisconsin and Michigan, Lake Michigan, but a very important one was a lake that has been dubbed Glacial Lake Agassi, that formed in northwestern Minnesota, or what is now northwestern Minnesota, and eastern North Dakota, and extending on up into Manitoba. This is an important stream because as it filled up, water started to spill out of its southern end and flow down what is now the Minnesota River into the Mississippi River and down to the Gulf of Mexico. By a little less than 11,000 years ago, the ice had retreated much more. Lake Agassi had grown considerably in size. By this time, the Chippewa River and its watershed was no longer a frozen tundra. There's probably forest moving in at first, maybe some spruce forest, and getting replaced shortly after this by sugar maple and a variety of pine, and then some oaks, and eventually even some prairie. And then by about 4,500 years ago, conditions had warmed to about what they are today, with very little glacial ice left, just remnants, such as on Greenland, which is still here today, islands in northeastern Canada, and in mountains to the west. And as a result, the rivers changed dramatically. So here are our rivers, the Red Cedar, the Chippewa, the upper Mississippi River, 21,000 years ago, and here they are today. At least this is the Chippewa River. Dramatically different, a dramatically different landscape, the landscape that we're all familiar with. So there's been a big change. Now you might ask, well, how do we know the story that you just told us about this aggradation of these glacial meltwater streams filling valleys with material washing out from the glaciers? Well, there's plenty of evidence in the landscape. One, throughout the Chippewa Valley, there are a number of sand and gravel pits, operations where aggregate is dug out for largely for concrete and for other uses. This is sandy, material with scattered gravels. And it has various sorts of features in it. It's called bedding, which is very typical of what braided streams create. And this material, there's lots of evidence that it's well over 100, maybe even over 200 feet thick in places in these valleys. So there's a lot of this material, which is glacial outwash. In addition, we can see in places where conditions are just right, the old stream patterns, the braided stream patterns that existed back when these were glacial meltwater streams. So here's a photo fairly close to Meridian, if you know where that is, along the Chippewa River, just to the north of it. We see here, there's the Chippewa River floodplain. And to the north of that, you can see all of these patterns here. All of these patterns, those are old braided stream channels, just like the ones I showed you in those modern glacial meltwater streams. Now, these braided stream patterns, they're not at the same level as the Chippewa River floodplain. They're on a flat surface that's about 30 to 35 meters, 100 to 100 and, pushing 120 feet above the Chippewa River on a flat surface that used to be the surface or the valley floor, if you will, floodplain of the river when it was a glacial meltwater stream. It's no longer the floodplain, though. It is now what is called a terrace. And this terrace has been given a name. It's called the Wissota Terrace. And the Wissota Terrace is a very common feature in the valley of the Chippewa River, as well as its tributaries, including the Red Cedar River. Here is Eau Claire. This is the university. This part of the university is called Upper Campus. Here is Lower Campus here. And this part of Upper Campus is on a very flat surface that's quite extensive. That is the Wissota Terrace. That's where, when the stream was a glacial meltwater stream, where the Chippewa River was flowing. Now, between the Wissota Terrace and the lower land, there is a very steep slope. That line there marks the top of that very steep slope, what is called a terrace scarp. And the height of the Wissota Terrace above the river here, well, it's about 35 meters. Very typical for the Wissota Terrace along the Chippewa. Now, if we look at maps, we can see the Wissota Terrace. We can see the Wissota Terrace scarp here along the Chippewa here on both sides, and you can make it out on its tributaries as well. Now, I and several students have used maps, what are called digital elevation models, to map the Wissota Terrace. So here is the top of the Wissota Terrace scarp, extending up from the Mississippi. We can trace it all the way to the Mississippi, up to the glacial terminus. It's not just along the Chippewa. You can also trace it up its tributaries, including on up the Red Cedar River, all the way up to the glacial terminus, here on the main stem of the river, as well as its large tributary, the Hay. So we have the Wissota Terrace, very extensive, a very prominent landform in the lower part of the Chippewa River watershed, along the main stem and along its tributaries. So that leads to a question then, as an earth historian, question I want to answer. When did this happen? When did the river cut down to a lower level, below that level where the river once was flowing, and create the Wissota Terrace? And always, when we ask a question like that, we also want to know why. What were the processes that led to this creation of the Wissota Terrace? Why did the river downcut? So to answer that, we need to go to the mouth of the watershed, where the Chippewa River flows into the Mississippi River. So here we have a number of features. I have some arrows there. I'm going to label those now with some text boxes. First, this arrow up here. Around 18 to 16,000 years ago, this is based on research that a PhD student at Madison did several years ago, now a professor at Indiana. He determined that the Mississippi River downcut below this level right here, this level, which would have been the level of the braided Mississippi River, down cut about 15 meters. It down cut to this level right here, where that arrow was pointing. And when it down cut, it left this as a terrace. That terrace has been called the Savannah Terrace. And the Savannah Terrace is the equivalent to the Wissota Terrace. It's just a different name given to the same landform in the Mississippi, upper Mississippi River Valley. Now the Mississippi, again, based upon existing evidence, stayed at this level right here for a few thousand years until about 13,500 years ago. And at that time, it down cut much more deeply, another 40 meters. So for a total amount of down cutting from this level of maximum aggradation of around 55 meters. That's quite a bit. 55 meters, that's around 175 feet of down cutting. And when it down cut, it left this as another terrace. That terrace is called the Bagley Terrace. Now you might wonder, well, why did this down cutting occur? Why did the Mississippi River, the UMR, the upper Mississippi River, why did it down cut at these times? Well, for the first time, the one between 18 and 16,000 years ago, that's still an open question. That's still being researched. Not sure why, but the one at 13,500 years ago, there's a much more solid hypothesis with a lot of evidence to back it up. And that evidence all points to this lake, Glacial Lake Agassi, that I showed you before. Glacial Lake Agassi started to form along the retreating edge of the Laurentide Ice Sheet around 13,800 years ago. It filled up this basin and started draining over a moraine that was a dam right there down the Minnesota River. As it rose higher and higher, more and more water started flowing over that moraine, and suddenly, evidence suggests it cut through that moraine rather catastrophically, and a big whoosh of water came down the Minnesota River. A big whoosh of water came down the Minnesota River, causing a lot of erosion of the Minnesota River Valley. In fact, it's believed that much of the Minnesota River Valley was cut during this time, and that incision continued on down the Mississippi River. So down cutting happened when that big whoosh happened, which was around 13,500 years ago. So there is the Minnesota River right there. Then, around 10,300 years ago, something changed. One big thing that changed is water coming out of Lake Agassi down the Minnesota River. That stopped happening. The Lake Agassi found another lower outlet. First, that lower outlet was to the Arctic Ocean, and then eventually it was to Lake Superior and on to the St. Lawrence Seaway. And that shut off about 10,300 years ago. And when that happened, at that time, slow aggradation started right here where the Chippewa River comes into the Mississippi. Slow, I say slow, because it wasn't something that was very rapid based upon existing evidence. It went on for several hundred and maybe even a few thousand years. But what it did, as it started grading here at the mouth of the Chippewa River, it created a natural dam, damming the Mississippi and creating Lake Pepin. Lake Pepin is a natural lake, the largest main stem lake on the Mississippi River. It exists because of a dam that is right here due to sediment that accumulated at the mouth of the Chippewa River. So that's sort of the background to what then happened to the Chippewa. And now, why is this all important? How is this significant for the Chippewa? Well, to answer that question, I'm going to show you a series of what are called longitudinal profiles of the Chippewa River. Here is a longitudinal profile or long profile. And what it just shows is sort of a side view of the river, how it drops in elevation from upstream to downstream. Here, where upstream on this figure is the glacial terminus. That was the LGM maximum extent right there. Drops from there down to right there. That's where it joins the Mississippi River. And so this is the river as it exists today, with 3 dams that are located along it. Some of these dams are built on waterfalls, such as at Chippewa Falls. There are rapids that are now underwater, Lake Wissota, and so on. But this is the profile of the river today. Now, here is the profile of the river with, above it, the long profile of the Wissota Terrace. That would have been the river slope back when the river was at its maximum level of aggradation, this glacial meltwater stream. For the most part, around 35 or so meters above the modern day river. So what happened? Well, what happened is between 16 and 18,000 years ago, the Mississippi River downcut. Now, the Mississippi River is what is called the base level for the Chippewa River and for all of its tributaries. That is, tributaries cannot cut lower than the big dog, than the big river. And in cutting down, it in essence pulled the plug on the Chippewa and created what is called a nick point. Imagine a nick point as being a kind of a waterfall, a very steep reach of stream. Now, it wouldn't have been a waterfall because this is sand and gravel doesn't stand up vertically, but it would have been a very steep reach of stream right there. And what happens with nick points is they erode. And they erode as they erode, they move up valley. And that is what happened with this nick point. And so by around 13,500 years ago, the nick point was, around 15 or so kilometers up from the Mississippi. It hadn't gone very far in that time. And it appeared to stabilize there. It probably got to this position pretty quickly and stayed there for a few thousand years. Exactly why it stabilized, we don't know. But we have abundant evidence that that is what happened. And then at 13,500 years ago, the Mississippi downcut much more, that additional 40 meters of downcut. And when it did that, it created an even bigger nick point that then started to migrate up the river. And so by about 12,300 years ago, the first minor nick point was about there, around 40 or so kilometers upstream, up the valley, and the bigger nick point at about 30 kilometers up the valley. This is important because right there is where the Red Cedar comes in. And so just as when the Mississippi downcut and lowered the base level for the Chippewa River, when the Chippewa downcut, it lowered the base level for the Red Cedar. Now this process continued but slowly. So by 10,000 years ago, which is 3,500 years after the big downcutting event happened on the Mississippi, the nick points were not quite 50 kilometers up the river. The minor one, the smaller one, and the major one catching up to it over time, but still not quite there. Then things picked up after 10,000 years. Between that and about 7,500 years ago, the nick point moved quickly farther upstream and it became flatter, which is what happens to nick points in sand and gravel material. At this point, it was at the confluence of the Eau Claire River, another large tributary to the lower Chippewa River. And then by around 4,700 years ago, the nick point was all the way to the glacial terminus. And subsequently, over time, this part of the river continued to downcut slowly but surely. Now, I didn't point out what was happening down here. As the nick point was moving upstream, down here, aggradation was occurring. This is the aggradation occurring that created the natural dam in the Mississippi River Valley that then backed up Lake Pepin. By 2,300 years ago, the river had downcut almost to its present level. Here in Eau Claire, much of Eau Claire, downtown Eau Claire, the university is built on this level right here. And here is the long profile today. So that's the evolution as best we know it right now for the lower Chippewa River. How it downcut from that level to which it had filled its valley with sand and gravel. But what's important is that as it downcut, it caused its tributaries to downcut in response. And so we have then the Wissota Terrace, not just along the Chippewa River itself, but going up its various tributaries, Plum Creek, Ogallie, the Red Cedar, and so on and so forth. Now, to put this into a different perspective, I'm going to put where we think the nick point was at these various times. So here is the first nick point that formed with downcutting of about 15 meters, 18 to 16,000 years ago. By 13,500 years ago, it was about 10 to 15 kilometers up the valley, and it stayed there for a while. And then a much bigger nick point formed with deeper incision on the Mississippi. That nick point then moved upstream just beyond the Red Cedar by about 12.3 thousand years ago. By 10,000 years ago, it was located there, close to the village of Caryville. Now, this is important here because what happened when the nick point was moving up here and it lowered the base level for the Red Cedar would have had a nick point moving up it sometime between starting around 12,000 or so years ago. And that's important because there's evidence that the Red Cedar, when it was a glacial meltwater stream right about here, split. Some of the meltwater came this way, some of it came over here and flowed down what is now Muddy Creek and through another valley, which is presently a dry valley. So there would have been branches of the Red Cedar. But apparently a nick point moved up the Red Cedar in response to the nick point passing by its mouth in this time frame, moved up here and downcut. So all of the flow ended up going in this direction, leaving these as abandoned glacial outwash filled valleys. Major nick point then was at the Eau Claire River by 7,500 years ago, and at the terminal moraine by 4.7 thousand years ago. So there we have it. There we have what we think is the history of incision below at Wissota Terrace level, instigated by incision on the Mississippi River, a process that took thousands of years to play out. In fact, as I'll mention later in just a bit, it's still playing out. I just want to zoom in to this map. So here we can see the Red Cedar River, and the Chippewa River right here. You can see very well the scarp of the Wissota Terrace on both sides of the valley of the Chippewa. We also see it along the Red Cedar here. But if you look closely, you can see below that some other flat surfaces that are above the level of what would be the floodplain, such as right here. You might be able to make it out right there. There's something over here that's below the Wissota Terrace, but above the river. And if you have really good eyes, you can even see it on the Red Cedar. But I don't have very good eyes, so we're going to zoom in. We're going to zoom in to the mouth of the Red Cedar here, and we're going to take a side view of the river made with some fancy software, an oblique view of the landscape. So this oblique view of the landscape was made using data that was derived with LiDAR. You may have heard of LiDAR. It's very data intensive elevation data acquired by lasers beamed down to the surface from airplanes and bounce back and get very precise topographic information. So a lot of data went into creating this map or this view, this oblique view, which can do using certain kinds of software. So here is the Red Cedar coming down here into the Chippewa River. Here is the Chippewa River floodplain. Here you can see a higher surface. This surface, however, is not the Wissota Terrace. Well, there's a little bit of Wissota Terrace right here. There's a little bit of Wissota Terrace here, but notice there are stream channels in size below the Wissota Terrace. Over here, notice there are surfaces that are below the Wissota Terrace there as well. And we're just going to take a little flight, if you will, up the valley. So here's just a little bit further up. There is that channel that I pointed out before. And notice these flat surfaces stepping down from, this is the Wissota Terrace. Here is the Wissota Terrace here. Notice some surfaces stepping down. We see a number of flat surfaces, stair-step surfaces, stepping down from the Wissota Terrace, down to the floodplain and back up to the Wissota Terrace. Follow on up, we see here Mahnamen. Here is Mahnamen, downtown Mahnamen over here. The Wissota Terrace, some of Mahnamen is on a lower surface here and an even lower surface there. Going on up, there is Lake Mahnamen. You see Tainter Lake in the distance. You see a large flat surface. This is where, at the time of the glacial maximum, some of the Red Cedar River flowed out in this direction and in this direction here. Continue on up a little bit farther. There is Tainter Lake. We see flat surfaces now, not completely flat. As we were saying before, some of this we're pretty sure is because of some strong wind erosion that occurred not recently, but thousands of years ago. But we still see the scarp of the Wissota Terrace, and we see lower terraces below it. And then finally, looking up the Red Cedar from near Colfax, we see the Wissota Terrace here, and we see some lower surfaces. Though those lower surfaces aren't much below the Wissota now. So what are these? Well, these are all terraces. And these are all terraces that are the result of the incision that occurred, similar to what occurred along the Chippewa River, but also occurred going up the Red Cedar River. Incision, downcutting, that happened episodically and stopped for a while and then recommenced, forming these stream terraces. So a little bit about how stream terraces are formed. First, how are floodplains formed? Here we see the floodplain of the Chippewa River. A floodplain forms when erosion occurs on the outside of meander bends on the cut bank, at the same time that deposition occurs on the inside of a meander bed called a point bar. And when these go along in tandem, a river shifts laterally. It shifts laterally, and what is created is what is called a floodplain. So we have a floodplain being created here, as in this case, the Chippewa River is shifting laterally. It's happening there, it's happening in the opposite direction over here, it's happening in this direction over there. A floodplain is being created by this river shifting back and forth. Now, if something were to happen that caused the river then to cut down, it would cut down below the level of this floodplain, leaving it as a terrace, much as what this higher surface here, what happened to it. That once was the floodplain of the Chippewa River, but the river cut to a lower level, leaving it as an abandoned floodplain or a terrace. And within the lower Chippewa River system and its tributaries, there are many, many terrace levels. We are still in the process of mapping all of these terrace levels. We have identified 6 terrace levels along the Chippewa River and its largest tributaries below the Wissota Terrace. There is an odd terrace called the Maxville, which is down here, which I'm not going to discuss, but there are many terraces, all of which are evidence that the river downcut to a level, stabilized, and then started shifting laterally back and forth, creating a floodplain, and then downcut again. So episodic downcutting separated by periods of floodplain formation. Here we get a more detailed view of all the different terrace levels along the Chippewa River and the Red Cedar, giving us a very complex picture of the history of these rivers. They did not just downcut in one fell swoop in response to the downcutting that happened on the Mississippi. Rather, they downcut, as I mentioned, episodically, then a period of time forming a floodplain, and then they downcut again. So we have then a complex history for a complex river. And I say a river because in my mind, all of these rivers, the Chippewa River, the Red Cedar River, and all of Chippewa's various tributaries are really all one river. They're part of one system. They're responding together. They affect one another. The Chippewa is influenced to downcut by the Mississippi. It caused its tributaries to downcut. But when those tributaries downcut, they in turn had an influencing impact on the main stem as well. And that's not the end of the story. This history that I described isn't something in the past. History is never really a thing in the past. History is just something we look to in the past, but we are at just one point in time in a trajectory. And when we look backward, we call that trajectory history, and the same is true of rivers. So here's the Chippewa River in Eau Claire, obviously. Here is Dell's Dam. The river is flowing this way. You might notice that the town is built right up to the river banks. Now you might think, well, it's because it's okay to build there. They're not going to get flooded because there's a dam here to control floods. Well, that's not a flood control dam. They're built there because they're built on, the city is built on terraces above the floodplain. There is very little floodplain of the sort I was describing here in Eau Claire. And why is that? Well, it's because down cutting here happened very recently, and the river hasn't had time to create a new floodplain. So Eau Claire is kind of lucky. It can be right up next to a river without fear of getting flooded very often. There's a photo of downtown Eau Claire from an airplane. Right here, just downstream of the dam, there is a nick point. Now this nick point happens to be in sandstone bedrock. The river is cutting down into bedrock there, but there is evidence of the river still down cutting here, right here in good old Eau Claire. Further downstream, the river is doing what rivers do. It's cutting laterally. And in some places, it's cutting laterally where its cut banks are very high cut banks that go all the way up to the Watershed Terrace. Other places, the cut banks are lower, cutting into lower terraces. But further downstream, the river is eroding material that was outwash that filled the valley. And it is slowly flushing this outwash out from its valley. Now, right now where that is happening is creating very interesting channel forms, such as this area near Meridine. Here's a little village of Meridine here, where the Chippewa River here suddenly breaks up into a number of different channels. And the reason for that is this is a region or a portion of the river, a reach of the river, in which there is a lot of sediment coming into the river from its banks, especially the high banks leading up to the Watershed Terrace. And the river has been forced to break up into a number of channels there. There is a view of that river that portion of the river looking downstream, going around what's called Chippewa Island. Here is the main part of the river. Here's another branch that goes over to Meridine, is right over there. So the river is still actively being affected by its past. And downstream from this region, suddenly we see a river that's a meandering river with very, very large point bars. Where is the sediment in those point bars coming from? Well, it's coming from here. Now that sediment is coming downstream, it's moving on down, some being deposited in point bars, but then being cut banks, but over time being moved downstream to where? Well, to the Mississippi River. This is the Mississippi River Valley right there. And here is where the Chippewa flows into the Mississippi River Valley. And here is that area of aggradation that I mentioned before. Why does that natural dam exist there? That natural dam is the result an immense amount of sediment that the Chippewa River has flushed out of its valley and that its tributaries have flushed out of their valley down to the Mississippi, overwhelming the Mississippi's ability to transport that material away, creating this natural dam. And this is a process that I mentioned before that created Lake Pepin. And it's also a process that is ongoing. Point to something, a little light colored area here on the photo. I'm going to zoom in, look at that. There it is. You may know what that is, you may not. What that is dredging spoil, or what some might call job security for the U.S. Army Corps of Engineers. A lot of barge traffic comes up and down the Mississippi River here. And the Corps of Engineers has to maintain a 9-foot navigation channel at least. And it's really hard right here. They have to do a lot of dredging here and further downstream. Because why? Because the Chippewa River continues to pump immense quantities of sediment out into the Mississippi River. This is the largest source of sediment to the upper Mississippi River that there is. It's a major pain for barge folks. Like I said, job security for some U.S. Army Corps of Engineers people. So the modern river is still being affected, still being impacted by what happened to the river in its past. The last 30,000 years are not irrelevant to the river today. So there we are. So here we're looking at this, in this slide, the Red Cedar River right here, flowing by a piece of terrace here, includes some Wissota Terrace and some lower terraces, cutting through here and joining the Chippewa just off the slide to the left. And here is the Chippewa here then, wending its way, going down to the Mississippi River. So as I said, the past, what has happened to these rivers in the past, is still affecting these rivers today. What these rivers are today are just one point in time in a trajectory that we might call history. But history is still real. History of these rivers is still relevant. So with that, I just want to end by saying, to understand the river, you need to know its history. With that, I'd be happy to take questions. Thank you very much.
All right, thanks so much, Doug. We do have a few questions coming in. If you have questions, folks, type them in the Q&A section of the little panel to your right. Don't put them in this panel that says chat. We cannot see that from where we're at, but we can see the Q&A. We've got a couple here. Well, one question, kind of a logistics question. Are replays available for participants who missed a session? Yes, these will be put up on the internet probably in a few weeks. I believe there might be some information over in your menu to the left about where and how you might get those copies of presentations. Doug, we have a question. I would like to learn more about fluvial geomorphology. Are there any courses to take online?
Oh, not that I teach. I teach a course, but it's a traditional course in classroom. However, you know, I do know that there are many universities, especially MIT, that has done a lot with online learning with their large MOOCs, and there are some fluvial geomorphologists there. Problem is, I don't know about the level. MIT probably tends to be a bit quantitative, but there is a lot of information online. So just Google it. But as far as I go, I do not teach fluvial online, and in part because it's a field science. We got to get out in the field, and you can't really do that online.
The best kind of science.
Yeah.
Another question. I love looking at the LiDAR maps. What are the best quality ones that show the most detail that are available for the public to use?
That's a really good question. You're in the wrong state. Wisconsin has not done a good job making LiDAR data publicly available. Minnesota has done a great job. they have a website where you can go and view LiDAR data online. There's an online web app, and you can look at maps for anywhere in the state. Iowa's the same. I think Illinois is the same. I'm pretty sure, I know Ohio is. I'm not sure about Michigan. For some reason, Wisconsin doesn't have this online data. It's spectacular. LiDAR, in some sense, for us earth scientists, it's a bit of cheating. We can see things we never were able to see. You know, you get detail on the ground, but you miss the big picture. Other kinds of traditional maps, topo maps, you can get the big picture, but you miss a lot of detail. LiDAR, you get it both. And we use it extensively. All the mapping of terraces, that's being done using LiDAR. But do check out Minnesota just to look at. You can see some spectacular landscapes. It's really amazing.
And I think what's happening in Wisconsin, I know that a few counties that I've worked with on different projects, counties are buying LiDAR data kind of by county. So check with your county land conservation department. They may have access to LiDAR data for your county.
That's a good point, Dan. Yeah, the LiDAR, getting the data and dealing with it, it's in our state, it's being done at a county basis. Other states have state programs, but Wisconsin does not.
Another question, can you explain more about the wind erosion on the east side of the Red Cedar?
The wind erosion. Yeah, I was actually going to include a little bit about that. We have, over the last 5 years, we and my colleagues, especially Gary Running and Phil Larson, the man I mentioned, have been looking at Aeolian landforms that are scattered around both in the lower Red Cedar and in the Chippewa River Valley. Landforms we would have never seen had it not been for LiDAR, because they're fairly subtle. Various kinds of sand dunes or sand sheets. And we've got some ages on them. I've never mentioned how I got any of these ages. It's using an analytical technique called optically stimulated luminescence. Basically tells us the last time a sand grain was exposed to the sun. So when it got buried or deposited. And we've done this on a number of Aeolian landforms, some small dunes. And they all sort of cluster between about, almost all between 10,000 and about 12 to 13,000 years ago. So it suggests that there was a period of time when there wasn't much vegetation on the landscape and there were really strong winds. And because they're in many places. And so what I'm inferring to be Aeolian wind modification north of Mahnamen there is just because of what we've seen and dated elsewhere. We haven't investigated there, but there's a lot of strangely sort of erratic areas that are slightly hummocky, that have no reason to be hummocky. And wind is the only process that we can invoke, that we know of, that would do that.
All right, next question. Where did the glacial melt end?
Glacial melt all went to the Gulf of Mexico. And is that where did it end?
That's where did the glacial melt end? I'm not sure if that's where did all the water go, or where did the glaciers pull back to?
Right. Well, I just wanted to say a little bit about that, because there are a number of earth scientists who are studying sediments out in the Gulf of Mexico and determining their age, so they can date it, knowing when, and looking at differences in their geochemistry, which is related to where the meltwater was coming from. It's related to the bedrock. And also it changes with the temperature of the water. So if it's like a big flush of very cold meltwater, there's a signature of that in the sediment. So they're been piecing together the meltwater history based upon what's out in the Gulf of Mexico in terms of the sediment. And then in terms of, when the glacier pulled out of the Chippewa watershed, as best we know, around 13 to 13,500 years ago. So at that time and after that, the Chippewa River system wasn't getting any meltwater at all. Mississippi was through Glacial Lake Agassi, but other than that, it was out of the upper Midwest.
Okay, and we've got time for one more quick question here. Do you have a favorite Nick point?
Do I have a favorite Nick point? I love them all.
not discriminating against the nick
Yeah,
points.
yeah. I mean, who doesn't love a great waterfall? A waterfall is just a spectacular nick point. But there are other less spectacular nick points, but they're really fascinating. And just a little aside, the Minnesota River Valley, which was supposedly carved by outflows from Glacial Lake Agassi, a lot of tributaries coming into there have pretty profound nick points. Some of them are waterfalls, some of them are just really steep reaches, and they're really interesting too, just along the side of the Minnesota River Valley. So a lot of favorites along there.
All right. Well, thank you so much, Dr. Faulkner, for presenting this information and sharing your knowledge and experience and research. We appreciate it. And thanks to everyone for attending. We're going to take a 15-minute break, and then we've got a plenary session at 2:30 from Tia Nelson, the daughter of Gaylord Nelson, a founder of Earth Day, is going to be talking at 2:30. So we hope you can return for that. Thank you, Dr. Faulkner. Thank you, folks, and enjoy the rest of the conference.
All right. Thanks, everybody. Have a great day.